It's recording.
Okay, great. All right. Okay, so let's get started by just reviewing very quickly the Ising model phenomenology. And I know for you guys here, this is superfluous, but let's do it anyway. So why do we care about the Ising model? Well, it's a prototype for discrete symmetry. Prototype. Discrete symmetry model. And we are mostly not going to do discrete symmetries in this course. Okay, we are basically going to do it today, and we're just going to use it to motivate looking at coarse graining and so on. And then we're going to move on and do other things. So it's a prototype. What we want to do is we want to understand how you set up calculations of order. I want to show you that that the dimension is important. To understand ordering. And then we're going to focus on the differences between systems with continuous and discrete symmetries. And I'm going to do this in ways that you haven't seen before. Well, of course, we're going to start off with the general setup as the usual thing. So here's our lattice, I equals 1 to n. I have a bunch of spins, plus or minus 1. I goes from 1 to n. So that's the system. The Hamiltonian is h sum over I, si, plus j sum over I and j, si, sj, and in principle there can be higher order terms. When we compute the statistical mechanics for n of these spins, we take the trace over all the degrees of freedom, e to the minus beta h, where beta is 1 over kbt, and by trace, what I mean in this case is the sum over S1 is plus or minus 1, sum over S2 is plus or minus 1, all the way up to sum over n is plus or minus 1. Okay, and then the free energy is defined like this. So the free energy is given by this trace. In other words, the partition function is just e to the minus the free energy over kBt. And if I want to compute expectation values, so we'll call these things thermal expectation values, then we would do, for example, if I make a site dependent external field H. So the Hamiltonian is sum over I, HI, SI plus J, sum over nearest neighbors I and J, SI, SJ. So I write the Hamiltonian like this. And so what I have here is a site-dependent external field. And so what that means is that the partition function is then going to be a function of the set of HIs. And of course, it will depend on J and the system size and KT and so on. And so then if I take the derivative of the free energy with respect to HI, so that is just going to be from here, this is going to be minus KBT times the trace of SI over KBT e to the minus beta h, and all divided by the trace of e to the minus beta h. So that just comes from writing down e to the minus beta h as what I've got over here on the left-hand side. And then when I differentiate with respect to h, that brings down this factor of SI over here. And then we have this minus KBT, and this factor of minus KBT is this factor here. So then if I put it all together, then what I get is the KBTs cancel out, and I just get minus the trace of SI times its probability distribution divided by the partition function, and the probability of finding the system in any state SI is given by e to the minus beta times a Hamiltonian as a function of all the spins divided by z. And so therefore we can read off that df by dhi is just equal to minus the expectation value of SI. Okay, so I think everybody here knows that very well. Anybody here not know that? So you came in late. Is this familiar to you? Okay, great. Okay, so that's the that's how we take expectation values in statistical mechanics. Now, what I want to move on to then is the phenomenology. So the thing that we're usually interested in is a measure of the global order, which is the magnetization. And so the magnetization is the sum from I equals 1 to n of the expected value of the spin at site I divided by n. So it's the average magnetization per spin. And that is just then given by minus 1 over n df by dh. And notice that I can get the sum of SI just by assuming H is a constant independent of space. So that's the magnetization. And it's possible to prove a number of analytical properties about the magnetization of the free energy, which I'm not going to go into right now. So in my RG book, section 2.6, we look at the analytic properties of the free energy per spin. So we'll call that F. Little f is the free energy per spin. And the most important ones of these is that f is less than 0. F is continuous. It's a function of h. It's a function of j. It's a function of t. Other things as well. That this is completely continuous, but it may have discontinuities in its derivatives. So the derivatives df by dh, df by dt, etc. These exist almost everywhere. And in particular, there can be discontinuities in df by dh. And since df by dh is proportional to the magnetization, those discontinuities have the interpretation as being first order phase transitions, as we discussed in detail last quarter. Okay, so in last quarter we talked about these following from these and other properties following from convexity. Okay, so next I want to talk about symmetry. So symmetry is going to play an important role in this course, much more importantly than it did last quarter. So let's just remind ourselves about the symmetry of the system. So let's discuss in particular time reversal symmetry. So there's other symmetries as well, but we're going to focus primarily on time reversal symmetry for now. So let's go back and look at the symmetry of the Hamiltonian that we've written down. So let me just write it out again for everybody. So we're going to write it down like this. So there's the Hamiltonian, and for those of you who came in late, this symbol here means I and J are our nearest neighbor lattice sites. Okay, so what I want to discuss now is what happens when we flip the sign of the spins. So the SIs, we're going to look at a transformation where we take SI and it goes to minus SI. So this you can think of as a spin flip symmetry or time reversal symmetry. Of course, in statistical mechanics, everything we're thinking of is equilibrium, but you can think of if the spin is pointing up now, previously it was pointing down, and so people use this terminology of time reversal symmetry, even though it's completely inappropriate. So if you look at this Hamiltonian, what happens when we reverse the signs of the spin? So let's have a look at up here. So if I reverse the sign of the spin, all spins, SI goes to minus SI, SJ goes to minus SJ, and so this thing just stays the same. But this thing over here changes sign. Well, I can restore that by making H go to minus H. So under the combination of two transformations, spin goes to minus spin, external field H goes to minus H, the Hamiltonian is invariant. So we can see that the Hamiltonian as a function of H and all these spins is invariant if I reverse the sign of H and I reverse the sign of all of the spins. So that's that is a symmetry of the Hamiltonian. So this is a symmetry of the Hamiltonian. And this has dramatic consequences because we can now follow through and compute what happens to the partition function. So the next question that we would want to ask is what happens to the partition function under this transformation. And we want to know that because the partition function governs all the thermodynamics. So let's just calculate it. So I'll start off with a partition function, and now I'm going to explicitly make H go to minus H. So there's the partition function. So this is the trace over all the spin variables being plus or minus 1, e to the minus beta times the Hamiltonian. And now I'm going to write in the arguments of the Hamiltonian. So it's minus h, j, and then the spin variables. So that's by definition is what I mean by z is minus z as a function of minus h. So whatever is in this first argument here, I make it minus, and so I've got a minus in here. That would change this h to minus h. Okay, now when we do the partition function, what is going to happen? The most important thing for you to realize is that this variable, the spin variable, is a dummy variable. All that means is it's a variable of integration or a variable of summation, and so we can make a change. We can make a change of variable. So let's go ahead and make that change of variable. So the strategy that we're going to do is to make changes of variable. And we're going to use the symmetry of the Hamiltonian. So let's go ahead and do exactly that. So I can replace the right hand side, excuse me, by saying this is just the sum over the SIs plus or minus 1. And now I've got e to the minus beta h. And now the Hamiltonian with minus h is the same as the Hamiltonian with minus SI, like this. So I can reverse the signs of the spins, and I can do that because I'm using the fact that this is a dummy variable. So in essence, I made a new variable. Let's call it S tilde, which is minus SI, and then I did a change of variable, and then dropped the tilde. Okay, so that's what I did in that particular step. Then I can use the symmetry. So now I use the symmetry. So then this Hamiltonian that I have up here, this Hamiltonian is by definition just the same thing as what I have at the top here. So I can write this now as the trace sum over these variables plus or minus 1 e to the minus beta times the Hamiltonian of now h, j, and si. And all of the minus signs have gone, and so that is equal to the partition function of h, j, and t. So basically what we've learned is that if I change the sign of h, it just gives me the same partition function. And so what that tells me, since the partition function is even in h, then that implies that the free energy, which as I wrote down before, is the free energy per spin, this satisfies f of minus h, j, and t is equal to f of h, j, and t. So the free energy is an even function in h. Okay, so why is that interesting? So this is interesting because it tells us that order is impossible. In other words, that we cannot possibly have ordered phases in statistical mechanics, or at least in this particular system. So let's see why that is true. So if f is an even function of h, then that means that the magnetization is a function of h. So nm is just by definition minus df by dh. And so that is equal to minus, and this is f as a function of h. So that is minus df of minus h by dh, because h is an even function. And that then is the same as df of minus h by d of minus h, putting the minus sign from here down into here. And then this is the same thing as minus n times the magnetization of minus h. Okay, so what I've learned then is that the magnetization as a function of h is an odd function of h. It transforms like that. Okay, so that's just, everything is exact. Now what we're interested in is systems that spontaneously break symmetry, okay, which means the system, as you are below a particular temperature, they spontaneously become magnetic, and being magnetic means that all the spins start to point up. Okay, that's not quite how it happens. And in the phase transitions course previously, we talked a lot about that. I'm not going to go into it in detail for now, but let's just leave it like this. So if we believe that this is true, so this is an exact result, which just followed from symmetry, then we can ask what happens when we set h equal to 0. So what happens if we set h equal to 0? Can we get spontaneous order? Because that's what this class is about. If we don't get spontaneous order, then we can all just go home. So let's just have a look. So we set h equal to 0. We set h equal to 0 because, of course, if I apply a magnetic field to a magnet, the spins are going to be oriented with a magnetic field. So there's nothing special about that. That happens in a non-interacting system. Here we've got an interacting system, and we are looking to see if it can spontaneously order. And if we set h equals 0, then what we've got before says that m of 0 is minus m of 0. And so that means that the magnetization in 0 field has to be identically 0. So yeah, it's spontaneous order does not exist, and we can all go home. Okay, so that's a sad fact of life, and what I've just shown you is that the order is not really possible. And what is the culprit here? Now, what I want to do now is explain to you that the culprit is something very surprising. So let's go to that. So the question is, what has gone wrong? And so we want to understand this, and the answer that I'm going to tell you is that the Boltzmann distribution is not the right distribution. So you learned on your mother's knee that the Boltzmann distribution is what happens in statistical mechanics, and it's not true. So we're going to think of this from the point of view of probability theory. Probability theory, probability distributions, I should say. So let's write down what is our probability distribution. So the probability distribution that we have is this: the probability of finding the system with a particular set of spins is, according to Boltzmann, e to the minus beta times the Hamiltonian of the partition function, or of the spins, and then it's normalized by the partition function of the n spin. So that is the probability distribution for finding a system in a system. Now we know that that the Hamiltonian, at least in zero field, is invariant. And so that means that P of SI is also P of minus SI. So the probability distribution is also invariant under change of spin, under change of a global flip of all the spins. And so what that means is that if I compute the expectation value of any spin, that's going to be the trace of whatever that spin is times the probability distribution of the spins, and that's going to equal 0. And it's going to be 0 because P is even in the spins and SI is odd. And so therefore we get 0. So this is just another way of thinking about this impossibility. Okay, so let's think a bit more carefully about what we are really doing here. So the conclusion is that the probability distribution cannot be the Boltzmann distribution. In an ordered state. And what we believe in the system of magnets is, when do you get an ordered state? Well, you get an ordered state when T is less than Tc. So this ordered state, at least phenomenologically, is going to be when the temperature is less than Tc. And we're going to see where that comes from in just a few minutes. So let me now explain to you why it is not why the Boltzmann distribution cannot be correct. So let's suppose that we consider all the states of the system. So this is the state space of the system, and I've drawn it metaphorically as a two-dimensional space, but it's every point in this space is meant to represent a configuration of the system. There's 2 to the n possible degrees of freedom, so this is a much higher dimensional space than just 2. And what we're going to what we saw over here. What we saw over here is the following: that if I've got a spin state which is up here, so this every point in this space represents all the spins in the system. Come on in. This is a space where each point represents this possible vector. So let's suppose that this is the state A, and then I've got another state over here which I'll call B, and this state is related to this first state by time reversal symmetry. So the vector SA is equal to minus the vector of spins SB. According to Hamiltonian, both of these states are equally likely. And so when we average over this whole space, we're going to get 0. So that's all that's why we got the answer that the order is impossible. So we got the result that order is impossible because for every state that we average over, that we sum over, there is another one with all the spins reversed, and M is minus M of that configuration, and so therefore when we add them all up, we get 0. So that's what we got. This is just a restating of it. So now we're going to do something that we didn't do before. Now what we're going to do is we're going to ask what happens when we add an external field. So now the probability of the system being in the state A is going to be different from the probability of the system when it's in state B. They're not going to be the same because the external field is going to preferentially interact with the spins here than the spins here. It's going to act in a different way to these different configurations because there's different numbers of spins pointing up and down. So the reason that they're not the same is because we have this term minus h times the sum over I, Si, in the Hamiltonian. So because I've got that term, without the field, those states are equally likely. When the external field is applied, then the ratio of these two states is going to be the following. Remember that this term over here, this thing over here, this is just n number of spins times the magnetization per spin. Okay, so that means that the PA over PB is going to be the following. Everything is going to be the same, except that I'm going to have an H n times m on the numerator, and I'm going to have an e to the this is e to the minus beta h n m in the denominator. So that is going to then give me that this ratio is e to the 2 beta h times n times m. So those states have different weightings, and the ratio of the probabilities is like this. Now, what we're going to be interested in is we're interested in infinite systems. Where n goes to infinity. So if I take n goes to infinity and I assume that h is positive here, then what you can see is that the probability of A becomes much greater than the probability of B. In other words, probability of B over probability of A is going to 0. And so in other words, the state, or rather the system, will be in the state A with magnetization M, regardless of the value of H, as long as H is positive, non-zero. So as long as H is non-zero, then that's true, and so therefore it's also true in the limit as I take H going to 0 from above. So it's also true in that limit. Okay, so that's an interesting statement. I can do the opposite thing. Suppose if H is actually in the negative direction, then what I'll get is that PA over PB will go to 0, even as H goes to 0 from below. So what this tells you is that the infinitesimal external field macroscopically biases the system as long as I take the thermodynamic limit. So this limit n goes to infinity is known as the thermodynamic limit. So, okay, so everything I said so far was true. So what does it tell you about the about the behavior of the system? So let's draw a picture then of what it means. So I'm going to draw here the value of H, and here I'm going to draw M. And so what is this? What have we learned from this? Well, at H equals 0, we expect M to go through 0, so we can get a behavior that looks like this. So as I take H going to H going to positive or H going negative, the M is going to be biased like that. So, but if I take the system going to infinity, then the amount of H that I need in order to bias M is going smaller and smaller and smaller. So if I say that this is a finite system, for a finite system, it will always go to 0 as I take the limit H goes to 0. But if it's an infinite system, then what can happen is that it can go like this. In other words, the limits do not commute. So the limit as n goes to infinity and the limit as h goes to 0 of df by dh divided by n, that limit is always equal to 0. Okay, so I take h go to 0, and then I take n go to infinity. So I limit h goes to 0 sums me here, and then I take the limit h n goes to infinity. I'm just going to stay there. If I take the limits in the opposite order, the limit as h goes to 0, after I've taken the limit as n goes to infinity of 1 over n df by dh, that thing can be non-zero. And so this is how you can get spontaneous symmetry breaking. This is how the system it is in principle possible to get a macroscopic order. And the situation that I've drawn here, this situation applies when t is less than tc. Okay, it doesn't have to do this. I didn't tell you that it must do that. I've told you that it can do that. The alternative is that it just does this. That as I take the system to be infinity, it can also just follow this pink line. And that pink line would be what happens when the temperature is greater than Tc. So this possibility is one that is consistent with all the analytic properties of the system. And this is how it's possible to have spontaneous symmetry breaking. If we have this picture that we have here, then what it's telling you is that the probability distribution for the spins cannot possibly be the Boltzmann distribution for t less than tc. So in fact, what has to happen is that it looks like this. Here is my phase space, my state space of all the states of the system. I'm going to take this state space and partition it. So all of these states here have magnetization that is positive. All the states here have magnetization that is negative. And then what we're saying is that if we're below Tc, then there can be either the probability distribution of the spins is non-zero in this region, and P is equal to 0 in this region, or it could be the alternative where I have it like this. So in other words, the probability distribution is 0 in this part of phase space, non-zero in this part, or 0 in this part and non-zero in this part. So this greater than or less than applies to both of these, to both of these things. So in other words, the probability distribution bifurcates. The probability distribution is not unique below Tc. Remember last lecture, I told you that emergence is associated with a loss of uniqueness. And emergence happens because there's a choice of possible states the system can be in, and it chooses one or the other. So now you're seeing exactly that here, that below Tc, the ordering, if it occurs, I haven't shown you that it does occur, I've just shown you how it can occur. That ordering is related to a non-uniqueness of the probability distribution. Now, what I want to do next, in this sort of lightning tour of the last quarter's results, is I want to now talk about the role of dimension. So what we've just discussed is how it is in principle possible for order to occur. Well, I didn't tell you exactly how this happens, the mechanism. So the question now I want to talk about is what is the mechanism? And in particular, well, I'm going to show you that the answer depends on spatial dimension. Now, in the last quarter's course, we discussed this by talking about the ergodicity time of the system. And then we also talked about it by looking at the correlation functions in different dimensions and seeing what the correlation functions look like. That was in one of the homeworks. So what I'm going to do now is I'm going to talk about the same thing. I'm going to talk about it from a completely different perspective. So so let me go to this section. So what we're going to do now is we're going to consider the Ising model in d equals 1 and d equals 2. And what I'm going to show you is that it's impossible for a phase transition to occur in one dimension, but it is possible for it to occur in 2 dimensions. So so let's talk about that. So now I'm going to follow in my RG book section 2.8.2. So what I'm going to talk about is what isn't sometimes known as the Landau-Piles argument. So let's think about a d equals 1 Ising model. And we're going to be looking at this in the x-axis like so, and I'm going to have my spins like so. That would be a configuration of my system. Okay, so what we're going to ask then is what happens at 0 temperature? So we know that the Hamiltonian is a minus j sum over I and j, si, sj. H is set equal to 0. So what do we want to do? Well, at 0 temperature, we don't have to worry about entropy. We just have to look at the energy of the system. So the energy of the system should be minimized in equilibrium. And we can see that there's an obvious way to minimize the energy. So if Si and Sj have the same value, whether it's plus or minus 1, and this whole thing here, this product will be minus 1. Sorry, this product will be plus 1. Then I multiply it by how many terms there are here, and then multiply by j. So the energy will be minimized in equilibrium, and that implies that Si must be equal to Sj for all I and j equals neighbor of I. So that means that actually the ground state of the system is going to look like this, or that. So there's two ground states, and they both have the same energy. Okay, so now let's just choose one of these states. So we're going to choose the up state, and the question we're now going to ask is what happens if I slightly raise the temperature? So now the temperature is just slightly greater than temperature than 0. Okay, so now what's happening is the spins are in thermal equilibrium, so they can flip with some finite probability, and so spins will flip. So let's ask. A picture of the system might look like this. I've got my up spins like so, and then maybe this spin over here has flipped, so this one is pointing down, and then all the other spins are still pointing up like that. Okay, so it could look something like the configuration could look like that. So what we're going to ask is what happens if n spins flip? So if n spins flip and point down, then what is going to be the magnetization? Well, that's going to be the magnetization per spin. So that's going to be the number of spins pointing up, but now there's n of them pointing down. So it goes like n minus n, and that goes divided by n. And now if I take the limit of n going to infinity, so that means the limit as n goes to infinity of this thing, and that is going to equal 1. So what we've just learned from this is that flipping n spins will not destroy the long-range order that we have at t equals 0.
I don't think it'll change the limit, but don't you also need a contribution from the down spins? Right, you've accounted for the fact that not all of them are pointing upwards.
Mm-hmm.
Then you should also subtract off another little n over big N.
Yes, you're right, and it doesn't change it doesn't change it. Yeah, thank you. Okay, so so the only way that that we can potentially destroy long-range order so I'm sneaking in this term long-range order. Long-range order just means that the spins are all pointing up, and this order persists macroscopically throughout the entire system. Okay, there's a more technical definition of long-range order involving what happens to the correlation functions as a function of distance, which we've talked about in last quarter, and I'll mention it again also here, but not today. So the only way that you could potentially get a non-zero result is that the only way that you can potentially destroy long-range order is that we ask the question wrong. So we said, what happens if n spins flip? Okay, n could be 100, could be 3, it could be 10 to the 50. Okay, even if I flip 10 to the 50 spins, it will still end up with them not destroying the magnetization. In order to destroy them, because I have to take the thermodynamic limit, the large system limit. So the only way we can potentially destroy long-range order is ask a different question. The different question we should ask is not what happens if we flip n spins, but what happens if we flip a fraction of the spins? And the difference is that the fraction will scale with the system size. So the only way that we can potentially destroy long-range order is if we flip a fraction f of the spins. So then if I take the limit as n goes to infinity of n minus f n over n, that's going to be a number that's less than 1. And that will be true even if that fraction is 10 to the minus 50. Okay, so a small fraction is not the same thing as a small number. Okay, so we have this is the dangerous fluctuation. So the dangerous fluctuation, and by dangerous, I mean one that can destroy order, is one involving a macroscopic number of spins. And it's a macroscopic number because this n is a fraction of the total number of spins. It's a fraction, not a number, and so it scales with n rather than just being a number that is of order unity. Okay, so now we know that's the dangerous fluctuation. Now we need to ask ourselves a different question. This is all well and good, but actually, once we're at finite temperature, we have to do statistical mechanics and not energetics. So the next thing that we have to worry about is we have to worry about entropy. We have to worry about entropy because T is greater than 0, and so we do not minimize the energy. Okay, that's only true at 0 temperature. That's only true in quantum mechanics. Quantum mechanics is 0 temperature statistical mechanics. Classical mechanics is 0 temperature statistical mechanics. So now we're at temperature greater than 0. So we need to look at what has happened to the entropy of the system. So we're going to consider the system's thermodynamics. Okay, so and where is this going to come from? Well, it's going to come from the entropy, i.e., how many different ways are there to flip these n spins. So that's the thing that we need to do. Okay, so let's see what happens in the ordered state. So in the ordered state, which is at t equals 0, the spins are all aligned like so, and so the entropy is equal to 0, and the free energy is just minus n times the interaction energy that each spin has with its neighbor, so you get minus nj. Okay, so now let's look at a different state. Now let's look at a state with a macroscopic number of spins flipped. So I'm going to look at a state that looks like this. So it's going to have all the spins over here pointing up like this, and then all the spins over here pointing down like that, and then in the middle here is an interface. So this might be I equals 365. This might be I equals 366, spin number 365, spin number 366, as it were. And there's a boundary between them because across this boundary there is a jump in the spin value. All these other ones, there's no jump in the spin value. As I go across here, there's a jump in the spin value, and so across this boundary there is a jump in the spin value. That's a configuration, and of course we're going to look at the system as it goes to n goes to infinity. So we're going to be doing that. Well, where can this interface be? So this interface. So this is of course a boundary or interface. So this interface can be at any location. So it can be, in other words, i.e. any of the n sites in the system. And we'll assume that the system has periodic boundary conditions. If I have periodic boundary conditions, I'm going to need to have two of these spins. So let's not worry about that for the moment. Then what I want to consider is the free energy difference between the system with an interface and the system with only with no interface. So let's have a look at what that is. We'll call this thing delta F. And the energy of the system is the same, except that if this is literally going to infinity on either side, the energy on this side and the energy on this side are the same, but the only contribution to the energy that is different comes from this boundary here. So I've got a spin in its neighbor pointing up and pointing down. And so that energy cost is 2J. So the energy cost of this thing is 2J. So the energy difference then is 2J, and so I've got that the energy is minus NJ plus 2J, and the way I can see that is it's minus n minus 1J plus J, if you like. So that's how you can see that's the energy change, and so that's the energy. And then what about the entropy? Well, the entropy is minus KB minus T entropy. The entropy is minus KB times the logarithm of the number of positions, and that's going to be n. So the entropy over here for this is KB times the logarithm of n. The free energy is equal to energy minus Ts. So the free energy difference, this delta F, is equal to 2J minus KBT times the logarithm of n. And so what that says is that if I now take t going to infinity, this term is going to then go to minus infinity. So what this says is that for any temperature greater than 0, delta F will go to minus infinity as n goes to infinity if there is a domain wall or interface in the system. So in other words, this state, a state with a boundary, a domain wall, an interface between an up region and a down region, this state is infinitely more preferred than the state with all the spins pointing up for any temperature above 0. Okay, so I'm 10 to the minus 300 degrees Kelvin above absolute 0. this state with a domain wall is preferred compared to the one where all the spins are below. So that's very, very strange. Zero temperature, all the spins point up, or all the spins point down. The minute I raise the temperature, even a tiny arbitrary amount, my infinite system will prefer to break into two domains. Okay. Now you're going to say that's obviously wrong, because if I take the limit n goes to infinity, each of these domains, this one over here stretches out to infinity, this one over here stretches out to infinity on this side. And those are infinitely large. Why wouldn't those infinitely large domains of up and down, why wouldn't they also split into two domains? And then they would. And then those domains would also split into two domains. In fact, every domain would split into two domains until eventually the system would reach a state where everywhere is domain. There will be no regions of order. So what will happen is now you continue this argument for the domain on the left, which is all up, and the domain on the right, and so what will happen is each domain will split into two, and so on and so forth, until there's no domains at all. And that means that there is no net magnetization. So what I've just shown you through this argument, which can be made rigorous, by the way, is that at any temperature T greater than 0, in D equals 1, it is impossible to have long-range order. And it is only true because we had domain walls, and so we could work out the energy cost of a domain wall. Suppose I had an Ising model, which was not nearest neighbor, but it was the nearest neighbor and the next nearest neighbor. Then the domain wall would not be just between two spins, it would be between three spins. But I'd still be able to do exactly the same argument. So basically, all that we needed for this argument to happen is that we needed that the interactions are short range. In this case, we used a nearest neighbor. But if it was next nearest neighbor or something like that, it would still work. And then you say, okay, fine, let's suppose the interactions decay exponentially. It'll also work. Let's suppose the interactions decay as a power law. It'll still work, but only if the power law behaves greater than 2. So in fact, if J as a function of the distance between spins goes like something like J over Ri minus Rj to the power sigma, then what you can prove is that if 1 is less than or equal to sigma is less than 2, then actually it is possible to have long-range order. Okay, so if the interactions decay sufficiently long, then this argument doesn't work. Okay, and why it's that distance is something else. If sigma is greater than 2, then the argument above works. and no long-range order. And can anybody guess what happens when sigma is less than 1? Anybody? So if this thing decays so slowly, it goes less than this exponent sigma is less than 1. Anybody got it?
Does the energy diverge? Or the energy per particle maybe diverges?
The energy per particle diverges. So the thermodynamic limit doesn't exist. And we saw that in last quarter. We looked at an infinite range model. And we solved that exactly. And that was a model of mean field theory. And there we had to scale the interaction in such a way that the thermodynamic limit existed. So the interactions are long range. Okay, so 3 minutes. Let's see if we can do 2 dimensions. Okay, so that's everything there was in 1 dimension. What about 2 dimensions? Okay, so now I've got my system that looks like this. But now I'm drawing the configuration space. So I might have, say, some region here that looks like this, where all the spins are up, and then the region outside of that where all the spins are pointing down. So I can have domains like that. So here is a domain of plus spins in a background of minus ones. Okay, so what is the let's suppose that the length of the boundary between the domains is n, little n, then the energy caused by having the domain is just 2jn. What about the entropy? So to calculate the entropy, what we have to ask is the following question. Let's suppose I start on the boundary. I start over here. What is the number of ways that I can draw this boundary, starting from here, going around like this, and coming back like this? So the question we have to ask is, what is the number of ways to draw the boundary? So we've got a boundary of n spins. Well, let's suppose that the lattice has coordination number z. Little z, not the partition function, but little z. So then we can say, well, I've got at each step, as I walk around this lattice, I'm making a circuit. I'm making a boundary of n spins. Each direction, I have z possible ways that I can go. So the number of boundaries that I can draw that have n spins is z to the n. It's not exactly z to the n. We can refine this. You might say, well, it can't really be z to the n because if I'm in this direction, I'm not going to go back. I wouldn't have gone anywhere. So we can say we'll just go in all the other directions than the one that we're pointing in right now. So this is an overestimate. So if you have to go in a different direction at each lattice site, then there are z minus 1 of these. Okay, so let's just use this as our estimate. then the entropy, the change in entropy due to having this boundary is going to be KB times the number of spins times the logarithm of z to the minus of z minus 1. So now, if I write down what the free energy is, the free energy is 2Jn minus KB T n times the logarithm of z minus 1. And notice that here I have an n here, and I have an n here. And that n came from that z to that came from that n over here. And so now you can see that now what happens as we take n going to infinity depends on the temperature. So if T is greater than this number, Tc, which is 2J over KB times the logarithm of Z minus 1, then delta F goes to minus infinity as n goes to infinity. And that means that the ordered state is unstable to thermal fluctuations. But when T is less than Tc, the the delta F is minimized by little n going to 0. In other words, the ordered state, the long-range order, is stable. And so this is fantastic. So the fact that I have a different number of possible places to put domain walls in 2 dimensions compared to 1 dimension means that now I have a way to have long-range order. Okay, so that's where we're going to finish for today. So what I showed you in today's lecture is we reviewed a whole bunch of things from our last quarter. We reviewed the Ising model. We reviewed the role of symmetry. We showed that symmetry can naively make it seem as if emergent order is impossible to have. And then we saw that that's happened because the Boltzmann distribution is not quite the same one as the ordered state. And we looked at this in a completely different way than we did last quarter by thinking about the biasing effect on 2 possible probability distributions for states of the system. And then what we did was we looked at what happens in 1 and 2 dimensions for the Ising model, and we saw that if the forces, the interactions are short range, then the ordered state is unstable firmly in 1 dimension, but is stable at least below a certain temperature, which we bounded in 2 dimensions. Now, when we have continuous symmetry, which is what we're going to start off with next week, there's going to be a fundamental difference in all of these arguments. Because what's going to happen is it's not spins are either up or down, and so there's a domain wall here. If I have a continuous symmetry, the spin here can differ from its neighboring spin by just an infinitesimal angle. And because it's an infinitesimal angle, that means that the behavior of the system, all of these assumptions that we made here in these calculations today, none of those go through. It's a very different type of calculation. We can do the same sort of thing, and we will do it, but it's a much different type of argument. Okay, so any questions about today's lecture? So for those of you who came in late, I recorded the lecture, and I will post on Teams the link to it. It'll be there for just for a few days until the university takes it down. So if you want, you can download it and then review it. What I'll try to do at the class suggestion is to remember to record all the lectures, and eventually I'll put them on YouTube, and then I'll never have to lecture ever again. Okay, any other questions? Okay, any of the people who weren't registered with this class last quarter did you guys, there's four of you, four of you, did you send me an email so you can either be an observer? Did you sign up for Teams? So, yeah, using that. Yep. If you haven't done it, please do so. If you want to join, if you haven't done any of that, send me an email. I can add you so you can see the Canvas website of the class. Teams is typically the way I will communicate with you, and you can communicate with me. I also sent out the first homework sheet. Well, it's not a homework. I sent out two homework sheets. One is called Homework Zero. Homework Zero is how to read a paper in 5 minutes. Okay, it's a very useful survival skill in graduate school. When you write your PhD thesis, you will end up with 300 citations in your PhD thesis. You'll have read all of those papers and be experts in them. How will you do that? You'll remember Homework Zero, and you'll know how to read papers really quickly and learn to understand them. It'll make you a better scientist. That's Homework Zero. If you want to send me a Homework Zero completed assignment, after you've looked at it, you can, but it's not something that's graded. And then there's a worksheet on second quantization. How many people here have done second quantization? Most people have, not necessarily all of you. Okay. If you haven't done it, how many people here have never heard of second quantization? Okay. Okay. Why haven't you heard of it?
Some undergrad.
You're an undergrad. That's no excuse. Okay. Okay. So you will learn about it, and so if you want to know more about it, look at the homework set. It will teach you how to do it. But if you want a bit of background to it, email me and I'll suggest a place where you can just read about it so you get the idea. The calculations are easy, but you just have to get used to using operators and things like this. And so there's a little bit of learning you have to do. Most of you have done it, but will not remember how to do calculations in it. And that's not a problem, because I happen to all the classes that I've ever taught this in for the last 20 years. So that's fine. Doing this homework set, which will walk you through all the things you need to know, won't take you very long. And at the end of that, you'll know more about second quantization than anybody who's taking quantum mechanics. Okay. Why do we care about it? Because later in this course, we're going to be using second quantization to look at interacting Bose-Einstein condensates. We're going to use it to look at the BCS theory of superconductivity. And if you're a student in my group, you will use second quantization even for classical problems to look at pattern formation in systems far from equilibrium using methods that come from second quantization. So, so it's very important to know second quantization, particularly if you're one of my students. Okay, if there's no other questions, then 2 o'clock, so go ahead.
Thank you.
So Johnny, if you want to have some, if you need to know about second quantization,